All the problems in Chapter 9 involve solving for static equilibrium, where we have the sum of the forces equal to 0 and the sum of the torques equal to 0. We'll start with a couple of simple one-dimensional problems, and then we'll do a couple of more complicated two-dimensional problems. Okay, so in this problem I've got two people carrying a heavy electric motor on a board. Each person lifts at one end of the board, and we want to know what's the weight of the motor based on the forces that each person applies. If I draw a picture, I've got one person at the left end applying 400 newtons of force, one person at the right end applying 600 newtons of force. And this is just arbitrary, which person I put on the left, which person I put on the right. It won't make a difference to your answer. Where is the motor? So we've got the motor here with its weight acting downwards, and we want to know how far it is from one end, so we'll solve for the distance from the 400 Newton end, and we know the total length of the board is 2.00 meters. Okay, so sum of the forces is 0. Notice that this force equation is a vector, so I need to do sum of the forces in the x direction is 0, sum of the forces in the y direction is 0. Now I only have forces in the y direction, so I can't use the top equation. So sum of forces in the y direction, I've got upwards 400 newtons plus 600 newtons, and downwards I've got the weight of the motor. Okay, so that means if I rearrange that, I've got 1,000 newtons minus the weight of the motor is equal to 0, so therefore the weight of the motor is equal to 1,000 newtons. Okay, so I've done the first part already. Now we want to know where along the board is the center of gravity of the motor. Well, I'm going to have to use my second equation now. Sum of the torques is equal to 0. So I'm going to have the torque from the 400 Newton force, the torque from the 600 Newton force, and the torque from the motor. Those all have to add up to 0. Alright, so I'm going to put my axis somewhere. Let me put it down at the left-hand end of the board. Okay, so now the torque from the 400 Newton force is equal to the force times the distance times the sine of the angle is our equation. So our force is 400 newtons. Our distance, now the 400 Newton force is right at the axis, so the distance between the force and the axis is 0. And what's the angle? Well, the angle between R and F in this problem is always going to be 90, and because my distance is 0, my torque is 0 Newton meters. Okay. The torque from the motor is going to be equal to the force of the motor, which is its weight, times its distance, which I don't know, times the sine of the angle between R, which is this line here, and F, which is the weight, and that's going to be 90 degrees. Okay, so I've got the weight of the motor times x times sine of 90, which is 1. So that's equal to 1,000 times x. Now I need to always think about the sign of the torque. So is it rotating clockwise or counterclockwise? If I put my axis here at the cap end of the pen and I pull down over here, my pen is going to tend to rotate clockwise. So that motor is going to give us a negative torque. Alright, only one more to go. 600 Newton force. It's got force, 600 newtons, times the distance, which is the whole length of the piece of wood, so 2 meters, and the angle again is 90 degrees. Sine of 90 is 1, so that gives us 1,200 Newton meters. Okay. So now I've got all my torques. Is this torque positive or negative? Well, again, if I put my pen down, rotate around the cap end, if I pull up at the tip of the pen, it's going to rotate counterclockwise, so that's positive. So sum of the torques is 0. I've got 0 minus 1,000x plus 1,200 is equal to 0. So that means 1,000x is equal to 1,200, or x is equal to 1.2 meters. Okay, so the motor is located 1.2 meters from the end with the 400 Newton force. Okay, let's do another one-dimensional problem. Now I've got someone standing on a diving board, and my configuration is a little bit different now. Now I've got the diver who has a weight of 500 newtons. So we know we've got 500 newtons down here standing at one end of the board. The diving board is of uniform cross-section and weighs 280 newtons. So if it says uniform cross-section, then that means that the center of gravity is going to be at the center of the board. So I've got a weight of 280 newtons halfway along the board, so that's going to be 1.5 meters long. So here's the weight of the board, 280 newtons downwards. Now we also have two forces coming from the supports. We've got one from this support over here and one from this support over here. This support, obviously if I have my diving board like this, I pull down here, this support will have to push upwards on it. Let's call it the force of the support. And this support over here is going to push down because this board is pushing up on there. So let's call this the force on the left. So we've got the force on the support and the force on the left-hand end, which we're meant to find from the problem. Alright, so same two equations. Sum of the forces in the y direction equals 0. There's no forces in the x direction. So we have upwards, only the force of the support. Downwards, we've got the force on the left side, minus 280 newtons, minus 500 newtons. And we don't know either of these two forces, so we can't do anything more at the moment. Next thing is to find the sum of the torques equal to 0. Set the sum of the torques equal to 0. We get the torque from the left-hand side plus the torque from the support plus the torque from the board, which is from this 280 Newton force, plus the torque from the diver, which is from the 500 Newton force. To get the torque, we have to pick the axis to be somewhere. Let's pick it over here. So if our axis is over here, then the torque from the support is going to be equal to 0 because our axis is there. And then we only have the other three torques. So the torque from the left-hand side is equal to the force on the left side, which I don't know, times the difference between the axis location and where the force is applied, which is 1 meter. And the angle here is 90 degrees, so sine theta is 1. And this torque would tend to rotate the object counterclockwise, so it's positive. So this is just plus FL times 1. Okay, torque from the board is equal to the force of the board, 280 newtons, times the distance between the board center and the support. So the board center is 1.5 meters from either end, and the support is at 1 meter, so we have 0.5 meters as our distance. Again, sine theta is 1. So this leaves us with 140 Newton meters. And this force over here, if our axis is here, this force would tend to rotate it clockwise, so it's negative torque. And the torque from the diver is the force of the diver, 500 newtons, times the distance between the support and the diver, which is 2 meters. And again, sine theta is 1, so that's 1,000 Newton meters. And again, it's a clockwise torque, so it's negative. So our sum of the torques equals 0. We have 0 plus 1 times FL minus 140 minus 1,000. So that means the force on the left side is 1,000 plus 140, or 1140 newtons. Okay, so there's the answer for part B. Now we can use that and plug it in up in this equation to get the force on the support. So the force on the support is equal to the force on the left side plus 280 plus 500. So that's equal to 1140 plus 280 plus 500, which is 1920 newtons. So the answer for part A is the force from the support point is 1920 newtons upwards, and that has to be equal and opposite to all the downwards forces. The force on the left-hand side is 1140 newtons. So pretty much the same method that we used in the first equation, just slightly different geometry of the setup. Alright, the most common type of problem you'll see is a sign problem, where you've got some sign hanging from a beam and a cable. So in this case, we have a whole bunch of different numbers here. We have a beam that's 1.5 meters long, so this here. It has a mass of 12 kilograms and it's hinged at the wall. The sign is uniform with a mass of 28 kilograms and overall length of 1.2 meters. So there's your sign there. The two wires supporting the sign are each 32 centimeters long. So each of them is 32 centimeters long and they're 90 centimeters apart. Okay. And they're equally spaced from the middle of the sign. What does that mean? That means that since they're the same length and the same distance from the center of the sign, they each carry the same weight. So they each carry half of the weight of the sign. Okay, so half the weight of the sign acts here, half of it acts here. And then we have a cable at the end that's 2 meters long supporting the beam. And so what we want to know is what's the tension in the cable and then what are the forces on the hinge. So on the hinge we have to have a force from the wall pushing outwards, we'll call it a horizontal force to keep it from falling into the wall, and we also have to have a vertical force upwards to keep the beam from sliding down the wall. So we have the tension force, horizontal force, and vertical force, 3 unknown forces, so I'm going to need 3 equations in order to solve the problem. Alright, so sum of the forces in the x direction has to be equal to 0. What do I have in the x direction? I've got my horizontal force going out from the wall, and I have the tension from the cable. I've got its x component. So tension in the cable is in this direction. I have its x component going in. So that tells us that the horizontal force is equal to the x component of the tension, but I don't know either of those, so I can't do anything there. How about the vertical forces? Okay, vertically upwards, I've got the vertical force at the hinge, I've got the y component of the tension, and downwards I have the mass of the sign, and I also have the mass of the beam. I need to put in a g there to make it the weight of the sign and the weight of the beam, right? Because it's got to be a force, not the mass. So I know the masses, but again, I don't know either of those two, so I've got 2 unknowns I can't solve yet. So we need to use another equation. Obviously, the only one left is the torque equation. So what's going to be providing our torques? Let's draw a simple picture here. So I've got the tension at one end. I've got vertical force and horizontal force. I have the 2 cables, each of them with half the sign's mass acting downwards. And I also have the mass of the beam. And where does the mass of the beam act? It acts halfway along the beam, so it acts somewhere over here. So mass of the beam downwards. So the beam is 1.5 meters long, so that's going to be 0.75 meters. If I look at my sign, 1 cable's at far end, so that's at 1.5 meters. The tension acts there, this force acts there. And then this cable here is 90 centimeters from the end, so it's going to be at 0.6 meters from the wall. Okay, so I have my distances for all the forces, and let's put our axis here. Why do we put our axis here? Well, we always put our axis somewhere where there's an unknown force, so I could put it either at this end or this end where I don't know the tension, and our best bet is to put it where we cancel out as many unknown forces as we can. So if I put it here, then the torque from both of these forces will be 0 because the distance is 0, and so then that's just going to leave us with 1 unknown torque from the tension. Alright, so we've got then the torque from the vertical and horizontal are 0, so we can just leave those out. We've got the torque of cable 1, we've got the torque of cable 2, we've got the torque from the beam, and we've got the torque from the tension. Alright, so torque from cable 1 is equal to the force, which is half the mass of the sign, times g, times the distance, 0.6 meters, times the sine of theta, and our angle here between r and f is 90 degrees. So sine of theta is 1. So the mass of the sign is 28. So we just plug in our numbers, and we get the torque from the first cable is 82.32 Newton meters. I'll keep a bunch of sig figs right now. And it's going to be a clockwise torque, so I put in a negative sign. The torque from cable 2 is going to be the same thing, except cable 2 acts at the end of the beam, so at 1.5 meters. So I get 28 over 2 times 9.8 times 1.5. Again, it's going to be a negative torque. I get negative 205.8 Newton meters. All right, final one going downwards is the torque from the beam. So it's the mass of the beam times g is the force times the distance at which it acts, 3/4 of a meter. And sine theta is 1 again. So I get 12 times 9.8 times 0.75. And it's also clockwise. So I put negative 88.2 Newton meters. All right, almost done. Just one more to go. So the torque from the tension is equal to the force of the tension, which I don't know, times the distance that the tension acts from the axis, which is the whole length of the beam, 1.5 meters. Now times the sine of the angle between the beam and the tension. So I need to know this angle in here. Do they give me this angle? No, they don't, but they give me enough information to find it with. So how can I do it? Well, let's draw my triangle over here. I'm told that this is 2 meters, and this side, the beam, is 1.5 meters. I want to know that angle in there, theta. So if I look at this triangle, I say, well, this is adjacent, that's the hypotenuse, so 1.5 over 2 is equal to cosine theta. So theta is equal to inverse cos of 0.75, which is 41.41 degrees. So our angle between the radius and the tension is 41.41 degrees. Okay, so I put that in. I get 0.992 times the tension force, and again, I need to find the tension force. So plug all that into the equation. So sum of the torques is 0, which is equal to 0.992t minus all these other clockwise torques. And rearrange it and solve. I get that the tension is equal to 379.35 newtons, which we should round off to 3 sig figs, 379 newtons. Okay, so that's the tension in the cable. Now I need my horizontal and vertical forces on the hinge. Horizontal force is just equal to the x component of the tension. So the horizontal force is equal to t, and the horizontal component is going to be cosine of 41.41. So plug in tension is 379 times cos of 41.41. I get 285 newtons. Okay, the last thing that we need to do is to find the vertical force. So to find the vertical force, I'm going to use this equation here. So if I look at this equation and rearrange it, I get the vertical force is equal to the mass of the sine times g plus the mass of the beam times g minus the y component of the tension. And if I look at my triangle over here, the y component of the tension is opposite to the angle, so it's going to be the sine. So this is going to be minus t sine theta. So the vertical force is going to be equal to the mass of the sine, which is 28 kilograms times g, plus the mass of the beam, 12 kilograms times g, minus t sine theta. T is 379.35 newtons times the sine of 41.41 degrees. And if I plug all that into my calculator, I get 141.08, and at 3 sig figs, that's 141 newtons. The last kind of problem that people like to give is ladder problems. So here I've got a ladder. Let me draw a picture of what it says we have. We have a ladder that's sitting with one end on a ledge and the other end touching a frictionless vertical wall. What does the frictionless mean? It means that there's no vertical force provided by the wall. The ladder can slide freely up and down the wall. We're told the ladder makes an angle of 53.1 degrees to the horizontal, and there's an 800 Newton guy who's a third of the way up the ladder. And what we want to do is we want to find the forces at the base of the ladder, and we want to find the minimum coefficient of static friction to prevent the ladder from slipping at the base. Okay. Okay, so what forces do we have? Well, we've got weight of the night, we've got the weight of the ladder, which we're also given. We're going to have the wall pushing out horizontally. There'll be no vertical force because there's no friction. We're going to have a normal force from the ground, and we're also going to have a frictional force, and the frictional force will be so as to oppose the ladder from slipping. The ladder would want to slip away from the wall, so the frictional force has to be in towards the wall. Okay, so we want to find the normal force and the frictional force. We've got 3 forces that we don't know and 2 forces that we do know. So it's just like our last problem. So the sum of the forces in the x direction equals 0. We've got a horizontal force backwards and the frictional force forward. So all this tells us is that the frictional force is equal to the horizontal force from the wall. So if we know one of them, we know the other. Sum of the forces in the y direction equals 0. In the y direction, I have the weight of the ladder and the weight of the night downwards. So actually, I put minus sign in front of those. And I've got the normal force upwards. So that means that the normal force is equal to the weight of the ladder plus the weight of the night. And we know both of those, so we can actually already get our normal force just from here. So the weight of the ladder is 180 newtons. The weight of the night is 800 newtons. So the normal force is 980 newtons. Okay, so we're partway there already. So we want to find the frictional force. We don't know the horizontal force, so we can't get it here. We're going to have to get more information. The only other equation we have is the sum of the torques is 0. So again, where do I choose my axis? Let me put my axis where I have the most amount of unknowns. So I'm going to put it down at the bottom of the ladder. So now I'm going to have, these 2 torques are going to be 0, so I'm going to have a torque from the night. I'm going to have the torque from the ladder. And I'm going to have the torque from the horizontal force. And once I find the horizontal force, that's just equal to the frictional force. All right, so the torque from the night is equal to the force of the night, which is 800 newtons, times the distance that he is from the axis. Now it says in the problem that he's 1/3 of the way up the ladder, and the ladder is 5 meters long. So he is at 5/3 meters, times the sine of the angle between the radius vector, which is this one, and the force. Okay, so I know that this angle in here is 53.1 degrees. The angle that I need to use in my sine theta is this one here. So this angle is 90 minus 53.1. So that's 36.9 degrees. So I've got sine of 36.9, and I get negative 800.57 Newton meters. And I put the negative in because, again, it would tend to rotate clockwise. Torque from the ladder, same sort of idea. I've got 180 newtons as my force. The ladder weight acts halfway along the ladder, so it's going to be 5/2, or 2.5 meters. And the angle is the same. So I'm going to get negative 270.19 Newton meters. Okay, last torque, the torque from the horizontal force. I don't know what it is for the force, so I just put FH. It's acting 5 meters away from the axis. And now I need to know the angle between the radius vector, which is here, and the force, which is going this way. And that's this angle here, which is just the 53.1 degrees. So I'm going to put sine of 53.1. And this torque tends to rotate, pull the ladder away from the wall counterclockwise, so it's going to be positive. So I get 3.998 times FH. And I want to add those all together and solve for FH. All right, so sum of the torques equals 0. So I get minus 800.57 minus 270.19 plus 3.998 FH is equal to 0. So that means FH is equal to, add up those two numbers, divide by 4 basically, I get 267.8 or 268 newtons. Okay, that's my horizontal force, and from this equation up here, it's also equal to the frictional force. So the frictional force is equal to that. All right, last part, part B, says what's the minimum coefficient of static friction to prevent it from slipping at the base? Remember, coefficient of static friction times the normal force is equal to the frictional force. I know frictional force and the normal force, so I can get the coefficient of friction is equal to the frictional force divided by the normal force. So it's 268 divided by 980, and I get 0.273, and there's no units for the coefficient of friction. All right, so if you can do those kind of problems, you'll be set for anything that we can throw at you from Chapter 9.